3I Atlas, an object from another star, just slipped past the Sun, and when astronomers measured the tiny extra push that made Oumuamua famous, they didn't find it. Not yet. Instead, they found something stranger, an object gushing the wrong recipe of ices, as if its surface has been rewritten by the galaxy itself. Stay until the end of the video to find out why a missing push is as telling as a detectable one, and how this interstellar visitor, 3I Atlas, might be hiding the quietest mystery yet. Now, before we go any further, I want to hear from you. Hit that like button, subscribe to the channel, and tell me in the comments where you're listening from, what time it is there. And honestly, what are your thoughts on this object? Help our community grow by sharing this video and tapping that like button below. Thank you for your support, and now, let's drift a little closer to the mystery. For centuries, comets have been our solar system's messengers. They come screaming through the night, their tails unraveling in light, carrying dust older than the planets themselves. Each one follows a predictable rhythm, a curve dictated by gravity's invisible hand. But once in a while, something arrives that doesn't belong. 3I Atlas is one of those things. The third confirmed object ever known to have come from outside our solar system, a wanderer from another sun. When it was first seen by the Atlas survey in mid-2025, astronomers expected a familiar dance: the brightening coma, the curling tail, the small adjustments that comets make as sunlight heats their surfaces, and jets of vapour nudge them slightly off course. These are the little irregularities that make each comet unique, like a fingerprint drawn in physics. Yet when the tracking data came in, something curious emerged. The comet was active, clearly venting gas and dust, yet its trajectory was astonishingly clean. It wasn't showing the measurable non-gravitational acceleration everyone had anticipated. Imagine a cosmic snowball gliding past the Sun. As sunlight warms it, frozen gases boil away, forming jets that push in tiny bursts. Even a whisper of vapour can impart a measurable thrust, changing its path by kilometres over the course of weeks. That's what astronomers call non-gravitational acceleration, motion not caused by gravity alone. In 2017, the interstellar object Oumuamua became famous for precisely that kind of mysterious acceleration. It had no visible coma, no tail, yet it sped up as though pushed by something unseen. The explanation remains debated to this day: sublimating hydrogen, outgassing dust too fine to detect, or perhaps radiation pressure on an unusually flat, shiny body. So when 3I Atlas arrived 8 years later, scientists watched carefully, expecting to witness that same subtle shove, perhaps stronger since this visitor did have visible gas and dust. They pointed the world's telescopes toward it: Hubble, JWST, ground-based observatories across Hawaii, Chile and the Canary Islands. They measured every photon they could, and the result? Almost nothing. A trajectory governed almost entirely by gravity, as though the comet were inert rock. The mystery deepened when JWST began to analyse its chemical composition. Spectral data from the near-infrared spectrograph revealed a coma dominated by carbon dioxide, far more than water vapour. On Earth, water ice is the most common volatile in comets. Carbon dioxide, while not rare, usually plays a secondary role. But here, CO2 was nearly an order of magnitude more abundant. It was as if the comet's recipe had been rewritten. 8 parts carbon dioxide for every part water, a ratio almost unheard of in our solar neighbourhood. That told researchers something remarkable. 3 Atlas must have formed in a region far colder than any of our own comet's birthplaces, perhaps near the CO2 frost line of another star system. And yet, that chemistry created another puzzle. CO2 sublimates readily at the temperatures 3I Atlas experienced near the Sun. The comet was venting vigorously, forming a bright coma with sunward asymmetry. Yet all that activity produced almost no measurable change in its motion. If the object were light and fluffy, like typical comet nuclei, that much outgassing should have shoved it slightly off course. But it didn't, meaning either the nucleus was far more massive than expected, or the jets were arranged in such perfect opposition that every thrust cancelled out. Astronomers ran models. They estimated the mass required to suppress an observable push, roughly 10 million billion grams, the mass of a nucleus about 5 kilometers across, larger than 2I Borisov, and far denser than the porous snowballs we're used to. But if the body were that heavy, it should have held its surface ices deeper beneath insulating layers, reducing visible outgassing. The data didn't add up neatly. Some suggested that cosmic ray processing had hardened the outer shell, turning centuries of radiation into a glassy crust that released gas through microscopic pores rather than open vents. In that case, the outgassing might be strong enough to create a bright coma, but too evenly distributed to produce directional thrust. Others speculated that the comet might be rotating rapidly, averaging out any forces before they could alter its orbit, or that its jets emerged symmetrically from opposite hemispheres, a natural balance, accidental but perfect. Each explanation had gaps. Each required a coincidence or a property we hadn't yet confirmed, and beneath every hypothesis lingered a quieter question. Could the absence of a measurable push be telling us something new about how interstellar comets survive the long journey between stars? By October 2025, 3i Atlas reached its closest point to the Sun, about 1.5 times Earth's distance. Most comets would have surged in brightness, their tails blossoming as sunlight stripped away layers of ice. 3 Atlas brightened modestly, then stabilized. Its coma grew more defined, but its nucleus refused to misbehave. It simply continued along its predicted path, like a disciplined traveller respecting every law of celestial mechanics. Then came a curious observation from the Swift telescope: faint ultraviolet emission from hydroxyl, a byproduct of water molecules broken apart by sunlight. Even though the comet was still far from intense solar heat, that meant water was escaping earlier than expected, possibly from shallow subsurface pockets warmed by sunlight filtering through the dust mantle. Another contradiction: water production implied activity, yet still no measurable acceleration. The numbers told one story, stability. The images told another, turbulence and release. Reconciling the two became the new obsession of cometary scientists. If you picture 3i Atlas now, imagine a dark, rough world about 5 kilometers wide, coated in billions of years of cosmic dust. It spent perhaps hundreds of millions of years wandering the interstellar medium, a frozen survivor of another planetary system's infancy. Cosmic rays bombarded its surface, altering its chemistry, sealing some of its pores, and turning others into microscopic vents. By the time it crossed paths with our Sun, it carried a scarred crust, one that allowed gases to seep gently but uniformly, like breath through cloth. That uniform exhale might explain the paradox. Instead of producing directional thrust, 3i Atlas released gas in all directions at once, generating a bright coma but little to no net motion change. The missing push in this view isn't an absence at all, it's balance, a natural equilibrium forged by time and radiation. And yet the story doesn't end there, because if that were the entire explanation, the measured ratios of carbon dioxide to water would still leave us puzzled. The CO2 dominance suggests that even deep layers are rich in volatile ices, untouched by the heating cycles that alter most comets from within. That means the body's internal temperature has remained astonishingly low for billions of years. To maintain that cold over interstellar timescales, the comet must have spent most of its life drifting far from any star, perhaps expelled from its original system by gravitational encounters soon after formation. It might have passed through dense interstellar clouds, absorbing radiation damage but little heat. What we see today could be the exposed fragment of a world that never truly knew warmth. When you watch a comet through a telescope, it's easy to imagine chaos. Jets erupt, tails stream, dust drifts away like smoke. But beneath that spectacle lies exquisite precision. Gravity dictates the dance, and even a small deviation stands out like a skipped heartbeat in a steady rhythm. For 3 Atlas, astronomers recorded every one of those beats. By September 2025, they had hundreds of positional measurements from observatories worldwide, each one plotted, compared, and checked against orbital models that accounted for the pull of the Sun, planets, and even the subtle tug of sunlight itself. The numbers aligned almost perfectly, so perfectly that any non-gravitational acceleration larger than 3 times 10 to the minus 10 astronomical units per day squared would have shown itself. It didn't. That upper limit, though invisible to casual stargazers, told a remarkable story. If the comet was outgassing as vigorously as JWST's spectrum implied, the lack of measurable thrust meant either an immense mass or a symmetrical venting pattern so balanced it bordered on impossible coincidence. Both options challenged expectations. One group proposed the nucleus might be a compact monolith, not a porous cluster of icy rubble. Imagine a mountain of cosmic stone, its pores sealed, its surface crust thickened by radiation. The jets we see would then represent only the thin outer skin boiling away, with the core remaining dense and unyielding. That would dampen any recoil. If true, 3i Atlas could be the densest comet ever recorded, 5 kilometers across but heavy enough to shrug off its own exhaust. Another team suggested an elegant alternative: geometry. If the active regions lay near opposite poles of the rotating nucleus, their thrusts might cancel over each rotation. A slow, steady spin, perhaps once every few hours, could average the forces into near zero. The comet would appear calm, even as it vented clouds of gas. Neither idea can yet be proven. Each remains a guess stitched together from light and motion. But together they underline the paradox that defines this visitor: a comet that behaves too perfectly. As the data circulated, the community's curiosity flared. Some remembered the debate around Oumuamua, when that earlier interstellar object seemed to accelerate without visible cause. Was 3i Atlas repeating the mystery in reverse, a visible cause without the acceleration? Into this conversation stepped Avi Loeb, whose name has become synonymous with bold conjecture. In early August 2025, his team released a short paper comparing the two interstellar visitors. Where Oumuamua had been oddly smooth and fast, 3i Atlas was messy and slow. But both defied simple models. Loeb speculated that if 3i Atlas later exhibited any delayed acceleration, perhaps subtle, perhaps directional, it could point to engineered structure or reflective surfaces interacting with sunlight in non-standard ways. Mainstream scientists treated the suggestion cautiously. The overwhelming consensus remains that 3i Atlas is natural, shaped by physics alone. Still, the discussion itself had value. It forced researchers to sharpen their measurements, to test every assumption about how light and gas push on an object to drift between stars. To understand why this matters, picture a spacecraft coasting through space. Even the tiniest puff of thruster gas will alter its path, a change computers can track across millions of kilometers. Now imagine trying to detect a thrust equivalent to the weight of a sheet of paper pressing on a car. At a distance of hundreds of millions of kilometers, that's what astronomers attempt when they look for non-gravitational acceleration. The math must be exact, and so must the patience. For 3i Atlas, the patience paid off. The near-perfect orbit tells us not only that its jets cancel, but that our understanding of celestial dynamics can reach breathtaking precision. Every observation refines the mass estimate. Every residual in the data teaches us something about its shape and rotation. Even absence becomes information. As one researcher put it, when the universe refuses to surprise you, that refusal is the surprise. Still, the comet does surprise in quieter ways. Its composition, CO2-rich, water-poor, suggests an origin far colder than our Kuiper belt. Perhaps in the frozen outskirts of another planetary system, where sunlight was a rumour and chemical reactions crawled at glacial pace. In that ancient nursery, grains of rock and ice merged slowly, building a small body that never came close enough to its star to melt. Billions of years later, a gravitational encounter, maybe with a giant planet, maybe with a passing star, ejected it into interstellar space. There it drifted, alone, between suns. Cosmic rays battered its surface, splitting molecules, rearranging bonds, turning exposed ices into darker, tougher material. By the time it reached our neighbourhood, its outer skin had become a fossil of interstellar weathering. JWST's spectrum showing an irradiated crust fits this tale perfectly. At this point in the video, imagine the camera slowly orbiting a digital model of 3i Atlas, a rough ellipsoid mottled with frost, glowing faintly where sunlight grazes it. The narrator's voice softens further. Think of it as a messenger from far away, a note in a bottle tossed across the galaxy. It carries within it the chemistry of another sun's outskirts, preserved like handwriting in ice. When we analyse its gases, we're reading that message one molecule at a time. What we learn might refine how we search for planets beyond our own. Because if comets like 3i Atlas are common, then planetary systems everywhere must eject billions of such fragments, each one a record of its birthplace. Every interstellar comet we detect becomes a sample return mission we didn't have to launch. By late October 2025, as it rounded perihelion, 3i Atlas passed through its most illuminated phase. Cameras captured its bright coma expanding, subtle jets flickering across the nucleus. Astronomers awaited even the slightest deviation in its orbit, perhaps a delayed reaction as deeper layers warmed. None came. Even after emerging from behind the Sun at the end of October, its motion remained obedient to gravity alone. That consistency now forms one of the most valuable datasets in comet science. By comparing predicted and actual positions, researchers constrain how gas release interacts with shape, rotation, and density. Those same models will help future missions plan intercept trajectories should another interstellar visitor arrive, and one will. Statistically, the next is already on its way, invisible still, crossing the darkness between the stars. It's worth pausing to appreciate what we're witnessing. For the first time in human history, we're not merely seeing comets from our own backyard, we're beginning to collect them from the galaxy at large. Each object, Oumuamua, Borisov, now Atlas, broadens the sample, challenges our assumptions and whispers clues about planetary birth beyond our sun. The missing push is part of that whisper. It tells us that the forces shaping these travelers can balance to near perfection. That in a universe defined by motion, sometimes stillness is the rarest state of all. The next few minutes of the script drift into contemplation. The voice lowers, the music thins to a single drone. Imagine the emptiness between stars. No planets, no warmth, only dust and stray photons crossing centuries of distance. In that void, 3i Atlas travelled for eons, unlit, unseen. Micrometeoroids chipped at its surface. Radiation painted it darker. Atoms escaped one by one. Yet the nucleus endured, locked in cryogenic sleep. When it finally met the pull of our sun, it was stirred awake for the first time in billions of years. Its coma blossomed, its tail unfurled, and still it moved as though nothing had changed. Perhaps that's the real wonder. Not that it's active or inert, but that it embodies equilibrium. Every puff of gas balanced by another, every motion answered. A natural symmetry achieved not by design, but by time. Scientists love paradoxes like this because they force precision. To explain a missing effect, one must understand every potential cause. Teams are now modelling the comet's spin state, testing how an irregular shape might hide acceleration within observational noise. Others are examining the size distribution of dust grains in its tail, hoping that particle dynamics might reveal clues about gas velocity and vent geometry. All these details, minute and technical, converge toward a simple truth. 3i Atlas behaves consistently with physics, yet pushes the limits of our ability to measure. In the quiet between words, picture the sun's light fading across the comet's surface. The jets subside, the coma thins. It will spend the next several months receding into the darkness, becoming once again a point of light against the stars. Eventually it will slip beyond the reach of our telescopes, carrying with it the data we gathered, the questions we asked, and perhaps a few we still cannot phrase. For those listening in bed, eyes half closed, that thought can be oddly comforting. An interstellar traveller passes through our neighbourhood, leaving barely a trace, yet altering how we see the cosmos. A whisper of gas, a fraction of acceleration, a story of balance. Nothing more, and nothing less. When we talk about a comet's journey, we often imagine drama. Icy cliffs cracking, jets bursting, tails unfurling across millions of kilometres. But for astronomers, the true excitement lies in the decimals, the faintest deviations that betray the invisible. For 3 Atlas, the numbers whisper restraint. Each observation reinforces the same truth. The comet moves as if sculpted by balance itself. That idea, cosmic balance, feels poetic, yet it's entirely physical. Every molecule that escapes the surface carries away momentum. If equal amounts depart in opposite directions, the net effect is nothing. No acceleration, no drift, no extra push. In that stillness we glimpse a harmony that nature sometimes grants without asking. By November 2025, new images began to arrive from large-field cameras and dedicated amateurs who managed to catch the comet after it re-emerged from behind the sun. Its coma looked softer now, a pale halo spread by solar wind. Spectra showed the same CO2 dominance. the same trace of water. No surprises. Yet each confirmation strengthened the puzzle. Months of heating should have awakened deeper layers, and if those layers held fresher ices, their uneven release should have nudged the orbit. But nothing changed. Gravity alone remained enough to describe its path. This quiet consistency has become its signature. Scientists call that an upper limit result, a way of saying, we didn't see it, but if it's there, it's smaller than this. And upper limits can be powerful. They set boundaries on the possible. For 3i Atlas, they tell us that any non-gravitational acceleration must be weaker than 3 times 10 to the minus 10 per day, about a millionth of what Oumuamua showed. That constraint refines models not just for this comet, but for all interstellar visitors to come. There's another meaning hidden here, one that stretches beyond physics. Every time we measure what isn't happening, we sharpen our picture of what is. Science advances as much by silence as by signal. When data fall quiet, the imagination listens differently. Instead of asking, what's pushing it? We begin to ask, what keeps it so still? Some answers come from chemistry. CO2 sublimation can be gentler than water outgassing, because its molecules are heavier, and its vents often deeper. If the gas seeps through dust rather than bursting free, the recoil fades to insignificance. The comet exhales, but without movement, like breath diffused through a scarf. The beauty of that image lies not only in its serenity, but in its truth, motionless activity. The JWST team continues to monitor subtle colour changes in the coma, hoping to catch shifts that might betray rotation. So far, the light curve hints at a slow spin, perhaps once every 8 to 10 hours, but even that remains tentative. If confirmed, it could explain much. A rotation of that pace would average any directional thrust over time, leaving the orbit unchanged. Once again, balance. Meanwhile, models of its interior temperature suggest the nucleus remains below, 180 degrees, even at perihelion. Such cold preserves the original ices. It means that when the comet releases gas, it's venting material untouched since the dawn of its home system. In every molecule streaming away, we sample the chemical fingerprint of another star's protoplanetary disk. It's cosmic archaeology by spectroscopy. Imagine standing on its surface, if standing were possible. The ground beneath would be brittle, a mixture of dark dust and frozen gases, so weak that a gentle tap might send grains floating away. Above you, the sun would shine brighter than any other star ever seen in that sky. For billions of years it drifted through night, and now suddenly a furnace fills its horizon. The ice beneath your boots begins to whisper, not roar. The vapour escapes sideways, wrapping you in a faint mist. You would feel no motion, only a subtle tremor as molecules leap into sunlight. That's the stillness astronomers see from afar. Back on Earth, observers translate that stillness into mathematics. Each observation gets logged, corrected for atmospheric refraction, compared to predictions, and fed into orbital solvers. When residuals hover near zero, satisfaction ripples through research teams. The models hold. Yet behind the satisfaction lurks a quiet ache, the desire for surprise. Science thrives on anomalies, and here the anomaly is absence itself. It's that emotional undercurrent that gives 3i Atlas its narrative power. In 2017, we were dazzled by the inexplicable acceleration of Oumuamua, and the world briefly flirted with the idea of alien craft. Now we face the mirror image, a comet that should accelerate but doesn't. Two extremes of mystery, bracketing a decade of observation. Between them lies a lesson in humility. Our theories work until they meet reality's patience. Some astronomers have joked that 3i Atlas is the universe's apology for Oumuamua. Here's your normal one, they say, just to prove the cosmos still behaves. But even this normal visitor bends expectations. Its composition is off balance, its surface chemistry defies local norms. If we call it ordinary, we're simply expanding the definition of ordinary to include the impossible calm of interstellar objects. From a storytelling perspective, this makes it perfect for nights like this. A listener drifts towards sleep as the narrator describes an alien snowball gliding through sunlight steady as a clock. No danger, no urgency, only mystery and equilibrium. Let's linger on what interstellar truly means. It means unbound. 3 Atlas is not tethered to our sun, its orbit is hyperbolic. That word, hyperbolic, simply describes a path that never closes, a curve that bends away forever. If you plotted it, you'd see a graceful swoop around the sun, then an escape into the dark. Its velocity ensures it will never return. We are witnessing a single flyby in cosmic time. One visit, one look. That shape carries poetic weight. Every comet born here returns eventually, looping again like memory. An interstellar one does not. It reminds us that most encounters in the universe are brief, that even celestial relationships can be transient. Astronomers estimate that objects like this pass through our solar system several times each decade. We simply miss most of them. Our detection technology is improving though. ATLAS, the survey that found this comet, stands for Asteroid Terrestrial Impact Last Alert System, but its wide-field telescopes are just as good at spotting outsiders. As algorithms refine, more will appear, fragments from alien systems crossing ours silently. Each detection teaches us how to listen better. With 3 ATLAS, the listening is literal. The faint spectral signatures of CO2, the near-infrared whispers of dust temperature, the radio silence of steady motion. We've learned that not all interstellar messengers shout. Some simply glide through, leaving mathematics in their wake. The missing push then becomes a metaphor. It's about restraint, about forces cancelling until only understanding remains. In a noisy world, there's comfort in that. The universe, for all its explosions and collisions, also composes symphonies of quiet. 3's ATLAS is one such movement, soft, precise, and unexpectedly peaceful. As you listen, perhaps lying in bed, eyes heavy, picture the comet shrinking in the telescope's field of view. Its tail thins, its glow fades. Soon it will vanish, not because it ceased to exist, but because it moved beyond our instrument's reach. Still, it continues, carrying our curiosity alongside stardust from another sun. For scientists, the next step is prediction. How will future interstellar comets differ? Will they all show this CO2 excess? Will any display a measurable non-gravitational push? Each new object will refine the statistics. If many share 3 ATLAS's compositional oddity that tells us outer disks of other stars are CO2 rich, if some show pushes and others don't, we'll map a spectrum of behaviour shaped by origin and age. In this way, a single silent traveller can influence decades of research. Absence becomes seed. Even as we gather data, there's an emotional layer that numbers can't express. For the astronomers pulling all-nighters at mountaintop observatories, each exposure carries wonder. They know they are photographing a visitor from beyond imagination, an emissary older than our species, older than Earth's continents. To measure its motion is to engage in conversation across light years, and when that motion obeys gravity perfectly, the conversation turns contemplative. Perhaps the message is simply, all is balanced. If you were to follow the comet outward in imagination, you'd pass the orbits of Jupiter and Saturn, then Neptune's pale blue distance. Beyond that lies the heliopause, the boundary where the sun's wind yields to the interstellar medium. Within a few decades, 3i Atlas will cross it, re-entering the silence from which it came. Its coma will freeze again, its gases trapped. The faint tail will dissipate, leaving a dark speck drifting between stars. It will remain that way until chance brings it near another sun, maybe in 1 billion years, maybe never. What will it see out there? Nothing our eyes could ever register, but perhaps the faint glow of galactic dust, the occasional flash of a distant supernova's echo. In that endless night, it carries traces of 2 solar systems, its birth and ours. For an inanimate object, that's quite a legacy. Somewhere around this point in the video, the visuals fade to a slow pan of the Milky Way, colours muted, stars dense. The narration softens almost to a whisper. Out there, you might say, are countless worlds forming and dying, and once in a while, they send us a gift, a frozen messenger that glides through our light, neither friend nor foe, simply present. The listener breathes slower, matching the rhythm. The mystery remains unresolved yet satisfying, like a lullaby built from data. As the weeks pass, the comet fades into the dawn sky. Observers track it a little longer, but by December 2025 it will be gone to all but the largest telescopes. Its legacy, however, is only beginning. Each recorded photon becomes a data point in humanity's expanding map of the galaxy. Each spectrum, a sentence in the story of how matter travels between stars. For scientists, 3i Atlas is already reshaping how we think about comets. For dreamers, it's proof that the universe still holds surprises gentle enough to lull us, yet profound enough to stir wonder. And for those of us lying awake under the same night sky, it's a reminder that stillness itself can be an event. The missing push is now a line in the scientific record. Non-gravitational acceleration 3's10 nyo per day 2, a number so small it feels almost poetic, a decimal whispering equilibrium. This absence defines the comet more sharply than any motion could. Because if nature can sculpt something that active yet so balanced, it means our understanding of outgassing, rotation and thermal physics is still incomplete. There are subtleties we haven't learned to hear. That's the beauty of astronomy. Every answer uncovers a quieter question. What shape must a nucleus take to vent evenly in all directions? How long must cosmic rays bake its surface before they harden it into symmetry? Is this perfection common among interstellar visitors? Or did chance produce it once and perhaps never again? Theoretical work continues. Supercomputer models run for days, tracing virtual particles leaving simulated surfaces. Some predict that rough, multi-lobed shapes naturally cancel thrusts. Others find that the right combination of spin axis and vent placement can mimic stillness. None yet reproduce the full calm observed in 3i Atlas. So the mystery endures, not loud but persistent, humming like background radiation. Meanwhile, JWST and Hubble prepare for their final coordinated observations before the comet slips beyond range. They will search for changes in the CO2-H2O ratio, hoping to see if deeper layers reveal a new mixture. If the ratio remains constant, it strengthens the case for a uniformly processed crust. If it shifts, it means the comet hides stratified layers, ancient snow over ancient stone. Either result will teach us something priceless about how planetary systems elsewhere evolve. That's the quiet revolution these objects bring. They let us perform chemistry on alien worlds without leaving home. Beyond the science, there's symbolism. The missing push mirrors our own search for meaning. We look for evidence of forces unseen, spiritual, emotional, cosmic, and often find none measurable. Yet the lack of movement doesn't mean nothing is happening. Equilibrium can be as revealing as action. A heart steady between beats still circulates life. A comet steady between stars still tells a story. When the sleepy cosmos shares tales like this, the goal isn't to resolve every mystery, but to dwell in that equilibrium, the space between knowing and wondering. To remind listeners that curiosity need not shout, it can whisper you to sleep. As 3 Atlas leaves the sun behind, it carries momentum enough to escape forever. Its hyperbolic arc opens outward, beyond the orbit of Neptune, toward the edge of the heliosphere. In 20 years, it will cross the boundary where solar wind yields to interstellar plasma. Beyond that, the Milky Way becomes its ocean again. It will drift for millennia, dark, unseen, its gases refrozen, its story archived in silence. If another civilization someday detects it, they might read the chemical scars we left on its surface, faint isotopic traces of our sun's light, the echo of our measurements. In that sense, the encounter is mutual. We mark each other. Imagine yourself aboard the comet now. The sun is a bright star behind you. Ahead, only the cold sprawl of space. The instruments have gone quiet. The jets are asleep. You feel weightless, unpushed, unpulled, perfectly balanced. That is the feeling scientists detected in numbers, and that is the feeling we can borrow for sleep. The comfort of drift without destination. Back on Earth, night falls over observatories from Chile to Hawaii. Astronomers close their domes, satisfied. The equations worked. The images are stored. Tomorrow they will begin again. Somewhere among those images lies the faint tail of 3i Atlas, a line of pixels that proves it was here. They smile at the data's precision and step outside into the real sky, where stars are imperfect and beautiful. The boundary between measurement and awe blurs. One researcher later writes, "Sometimes I think the universe sends us lullabies disguised as comets." It's easy to agree. In future years, textbooks will cite 3i Atlas as the first interstellar comet with well-constrained non-gravitational limits and a CO2-rich composition. Students will memorize the numbers, maybe without feeling the quiet wonder behind them. But for anyone who followed its passage in real time, the memory will linger. A streak of light that obeyed every law yet defied expectation. The missing push will remain its signature, like a rest note in music. the silence that defines the melody. Now, as this story winds down, let's gather the threads. We began with a mystery, a comet from another star, bright and active, yet moving exactly as gravity dictates. We learned that the missing push is not a failure of detection, but evidence of harmony, jets in balance, geometry aligned, perhaps density greater than imagined. We saw how its chemistry, rich in carbon dioxide, tells of formation in deep cold and eons of radiation hardening. We traced how scientists measured its every flicker, confirming absence with precision finer than imagination, and we followed it outward, past the warmth of the sun, back into the silence between worlds. All of that from a speck of ice only a few kilometers wide. So what can we, lying here under our own ceiling of stars, take from this interstellar traveller? Maybe it's the reassurance that the cosmos runs on balance as much as on motion, that for every explosion there is a calm, for every acceleration, a stillness, that even when nothing seems to happen, patterns are forming quietly. Or perhaps it's simpler. We are capable of noticing subtleties so faint they almost don't exist. In that noticing lies humanity's genius, the ability to find meaning in decimals, beauty in data, peace in precision. Out there, 3i Atlas continues its long glide into darkness. The sun shrinks behind it, the Milky Way rises ahead, its surface cools, the gases freeze, and the silence it carried from the void returns. No engines, no thrusters, no measurable push, only equilibrium. And that perhaps is the universe's gentlest lesson, that balance itself can be a form of motion, and quiet a form of revelation. So as you drift to sleep, let that stillness reach you. Let the missing push become your breath, steady even, unhurried. Because somewhere beyond the edge of sight, a comet from another sun is doing the same.